All right, chapter 12, Congruent Triangles. So let's just break down that name real quick. That word congruent, that's one that we're going to be seeing for the years to come in high school, one you've probably seen since middle school or maybe even before. But the word congruent, many of us just associate it with the same, or mistakenly as simply as just equal. And I've mentioned it before in class, but there is a big difference between two things being equal and two things being congruent. Equality, or equal, deals with a single measurement. And so, for instance, if I was to talk about this expo marker, I could measure its length, and it could equal the length of another expo marker, right? That's a single dimension. But there are obviously a lot of other ways that I can measure these objects. And so when I talk about two expo markers or two objects in general being congruent, not only would their length be congruent to the other length, but also say the circumference of the marker itself, its diameter, its radius, the volume of ink in here, the size of the lettering, and obviously the more complex an object, there are a lot more measurements that can be taken. And it's not just as simple to say that they're the same. When two things are congruent, literally every measurable aspect about one object is going to be the exact same as the other. And it's a very, very deep statement. And so early on in mathematics, when we talk about congruency, we usually keep it simple so that there are very checkable ways to make sure that the two objects are in fact congruent. And we usually start off with like segments. And segments are boring because there's really only one way to measure a segment, and that's its length. And so most people just start associating equality with congruency, but it does go deeper. The more dimensions the object, the more parts of that object have to be the same or equal. And so this is kind of the next step up from segments being congruent, and that we're dealing with triangles. It's a two-dimensional shape, but it's also limited in the number of ways that I can measure a triangle. And so it keeps it compact enough that we can confirm that the two triangles are in fact going to be congruent or the same as each other without having to do so much work in achieving that goal. So that's what congruency means when we talk about two triangles being congruent. Every measurable aspect about each of those triangles has to be the same. And so we'll go a little bit more in depth into that definition moving forward. So in this first section, angles of triangles, that's the name of it, but we're going to talk about two different ways to classify or name a triangle. And you'll be familiar with most of these, hopefully. So the two ways we're going to talk about. Here's the first of which, classifying triangles by side length. Now, classifying, again, is just a fancy way of saying how to name something, how to group something. And you've probably seen some of these names before. Scalene is probably the oddest in the bunch. You may or may not have seen this one. That means that in a given triangle, none of its sides are congruent to each other. We call that scalene, right? Isosceles, you've likely seen this one before, and many of us jump to like, oh, two sides in that triangle are congruent to each other, and that's absolutely true, but it's at least two sides, which means I could have all three sides, like this triangle, being congruent to one another. This is still isosceles, for the record. The definition of an isosceles triangle is at least two congruent sides. And so if I found two congruent sides in this triangle, it's automatically isosceles, whether or not it matches the third side. Okay, and then again, one that you've probably been familiarized with, equilateral. Literally, this breaks down as equal side lengths. Okay, that word lateral means side, right? So equal sides. All three of the sides have to be congruent in order for it to be named an equilateral triangle. Some of the problems that you'll come across in this section will deal with how to classify a triangle by its side length, and you're basically looking for one feature. Do the sides have congruent lengths? Okay, and so in this case, if I know that this length here is 8 units, this would also have to be 8 units in order for this to be considered isosceles. I would have to show in this triangle that none of the three sides match each other. In this one, all three sides would have to be the same. Okay, all right, so the second way to classify triangles. The second way to classify triangles is by their angles, their angle measurement. And so again, classifying just has to do with names. And so there are 4 different names that you'll come across. Some you're familiar with, some maybe not. Most of us are familiar with right triangles at this point. We've definitely done that quite a few times this year. Simple enough, it has a 90-degree angle. And an interesting proof that happens in Math 2, we've talked about it in this class as well, but an interesting proof is that if I have one 90-degree angle in a triangle, could I have two 90-degree angles? And the answer is no. And the reason why is that in a given triangle, based off something called the Triangle Sum Theorem, all three angles in any triangle have to add to 180. Well, if I had two angles that were 90, that's all 180 degrees right there, and I'd have nothing left over for the third angle. So in a given triangle, it's impossible for one angle to be, for there to be more than one angle at 90 degrees. So a right triangle just simply has the one. Okay, and you usually see it with that box. Okay, two others that you've probably seen before, acute and obtuse. Acute just means that all three angles are under 90 degrees. Most people think associate acute with it's acute, it's smaller than 90, so it must be cute. I guess that works for some people. But in any case, an acute triangle means all three angles are under 90 degrees. For an obtuse triangle, that means one angle is over 90 degrees. There's one obtuse angle. It is impossible for there to be two obtuse angles for the same reason there can't be two 90-degree angles in a given triangle. So in both these cases, it's just one angle ends up determining the name or classification of that triangle. If one is over 90 degrees, like say 120 degrees, then that's an obtuse triangle. If one of the angles happens to be 90, that's not acute because it's not less than 90, but that makes it right. Okay, so you've probably seen these ones before. The one that maybe you haven't seen is this one. Lots of vowels. It's pronounced equiangular. Equiangular. And so what that means is much like equilateral, and there's a reason why I grouped these two together. Much like equilateral, this one deals with angles, and literally this breaks down as equal angles. All three of the angles inside this triangle have to be congruent to each other. Okay, and there's actually a very unique form of this, and there's only one possible solution for this. And the way we know that is that for every triangle, this is based on the Triangle Sum Theorem, for every triangle, all three angles have to add to 180 degrees. Well, if I know that all three angles are equal to each other, that means I could just divide 180 by 3, and each of these three angles has to be 60. That is the only possible way that they could be equiangular. So if you want to throw that in your margin, that's the only case for that. The only equiangular triangle is a 60, 60, 60 triangle. Okay, and there's another reason I grouped these two together. Equiangular triangles have to be equilateral. Equilateral triangles have to be equiangular. So these two go hand in hand. This is a unique triangle. Now, I could have different sizes of this same triangle where they have different side lengths, like this could be 3 miles or it could be 3 millimeters. Okay, so the size, the equilateral length, all three would have to be equal, but they would just be depending on what the size of the triangle. But no matter how small or how big it is, all three angles will have to be 60 degrees. That's a definitive fact. An interesting thing to throw in the margin if you have the room. So I'm going to skip over a couple of the examples. I'm going to talk through this first one, but the second video will deal with how to solve them. So the first example that we see here, again, I'm just going to talk through it. We're asked to classify a given triangle by its sides. So again, just to remind you, there are two possible ways to classify or group a triangle, either by its side length or by its angle measures. This one asks for sides. So in the second video attached to this, we're going to go on how to actually go about classifying something based on these coordinate points. Spoiler alert, we're going to be using the distance formula. But that's how we would go about classifying it by its sides. We would have to know side length, and we're looking for two sides or more to be congruent or equal to each other. And then determine if it's a right triangle. Now, the second part, determine if it's a right triangle, is actually an angle classification. And we're looking for a single 90-degree angle. And here's the spoiler alert again for this one. The only way I can have a right triangle is if the Pythagorean theorem works. This formula only works for right triangles with a 90-degree measure. And if this happens to be a right triangle, this will have to be true, whatever those side lengths are, A, B, and C. So that's the strategy for solving this one, but I wanted to skip over it and go into our theorems before I jump into the second video. So here's that theorem that I quoted a couple of times, the Triangle Sum Theorem. Many of us, for whatever reason, have this inherent knowledge. We kind of come into high school with this known in the background, whether you learned it in middle school or wherever. But the Triangle Sum Theorem simply says that no matter what kind of triangle I have, no matter how crazy it looks, all three angle measurements have to add to 180 degrees. That's in any triangle. Right triangles, obtuse triangles, acute triangles, equilateral triangles, scalene triangles. It does not matter. All triangles, the angle sum has to be 180 degrees. And many of us already know that for whatever reason, but that's one that just is now formalized in our notes. And we'll work with that moving forward. This comes up quite a bit. And the last theorem of this section, exterior angle theorem, it's kind of based off this guy right here. But if you were to have a triangle, any triangle, and extend one of the sides, so AC, the side of this triangle right here, it's extended off into the distance. This exterior angle, angle 1 right here, this exterior angle made outside of the triangle, that's why it uses the word exterior. The exterior angle made outside of the triangle has to be equal to the sum of the other two angles. Okay, so let me break that down again. Any exterior angle I have, and I could extend off different sides of this triangle and create different exterior angles. That's totally possible. But in this case, based on this drawing, this angle 1, this exterior angle created by extending a side AC, is going to be equal to the sum of A and B, the other two angles inside the triangle. Why is that the case? This has to do with linear pair. That angle 1 right here is an exterior angle. It's a linear pair with this little guy inside here, angle BCA, this angle right here. These two have to add to 180 degrees. Well, based on that, since in the Triangle Sum Theorem, A, B, and C have to add up to 180, that's why I can take the supplement of this guy to get this exterior angle, and that's why this ends up being true. Okay, so we'll jump into that in our next video on how to go about solving each of these examples based on these theorems. But this is our start to chapter 1, our final unit of the semester on congruent triangles. And here was our section on angles of triangles.